This video continues our presentation of Chapter 13, Fundamental Equilibrium Concepts. In this video, we are working on Section 13.4, Sample Problem Number 2 from the lecture handouts. Question 2 states that at 503 Kelvin, the equilibrium constant Kc for the dissociation of N2O4 gas has the value of 40. We're asked to calculate the fraction of N2O4 left undissociated when 1 mole of this gas is heated to 503 Kelvin in a 10-liter flask. Let's start by writing the balanced chemical equation for the reaction. And go ahead and start to set up our ice table. We also want to write the expression for K. Since we're given a value for Kc, we're going to set this up using concentrations rather than partial pressures, even though the reactants and products are in the gas phase. So we put the concentration of the product, NO2 gas, squared because of the coefficient 2 in the balanced chemical equation, divided by the concentration of N2O4. We now need to start filling in our ice table. We're told that we're going to put 1 mole of N2O4 in the flask at 503 Kelvin, and the flask has a volume of 10 liters. Since molarity is moles over volume, we can calculate the concentration of the gas as 1 mole divided by the volume of the flask, which is 10 liters, gives us a concentration of 0.100 molar N2O4. This is going to be the initial concentration of our N2O4 gas. We'll assume that there is no nitrogen dioxide gas at the beginning of the reaction. For our change row, we need to decide in which direction this reaction is going to shift to reach equilibrium. Since we have only reactants and no products, we're going to have to shift towards products to reach equilibrium. So we'll use minus x as the change for our reactant and plus 2x for the change for our product. Again, the equilibrium row is always the sum of the initial and the change rows. We now want to plug these equilibrium expressions into our Kc term. So we have 40 is equal to the concentration of NO2 squared. Our equilibrium concentration of NO2 is 2x, so we're going to square that term, and then divide that by the concentration of N2O4, which is 0.1 minus x. Unfortunately, we don't have a perfect square in this case, so we're going to have to do a little more algebra. Multiplying the denominator by 40, and then combining terms and getting everything on one side, we have 4x squared plus 40x, when I move it over to the other side, minus 4. And this is going to be equal to 0. You may recall from algebra class that we can use something called the quadratic formula to solve these kinds of equations. The quadratic formula says that if you can write your equation in the term of ax squared plus bx plus c is equal to 0, x can be determined as negative b plus or minus the square root of b squared minus 4ac all over 2a. The plus and minus term here tells us that we're actually going to get two answers when we solve this equation. In other words, the answer has two roots, only one of which will make physical sense, however. I'm going to continue to the next slide to give us some more space. So again, we're going to be working with the quadratic formula. So when we plug this in, our b value is 40, so we have negative 40. Sorry, I was a little bit lax with my significant figures here. Plus or minus the square root of b squared, so that's our 40 squared, minus 4. A has a value of 4 as well, and c has a value of 4. We're going to divide that by 2a, and our a value was 4. So although it's a little bit ugly, we can plug this into our calculator, and we'll get values of x 0.099, as our only positive root. We do get a negative root of negative 9.89, but that doesn't really make any sense in the problem. So that means our value for x is 0.099. Now we need to go back and answer the question. Our equilibrium concentration of N2O4 was 0.1 minus x, which gives us a value of 0.001 molar. Our equilibrium concentration of NO2 should be 2x, or 0.198 molar. The question actually was what fraction of N2O4 is undissociated at the end of the reaction. So what we're actually looking for is the amount of N2O4 left at equilibrium compared to the initial amount of N2O4. So when we plug that in, we find that the fraction is 1/100th, or 1%. Let's look at part B of this problem. We have the same reaction and the same equilibrium constant, but we're asked what would be the new result if the volume of the flask was reduced from 10 liters to 2 liters. Again, let's start with our balanced chemical equation. And a new ice table. The Kc expression has a value of 40 and is going to be the concentration of NO2 gas squared over the concentration of N2O4. We could start from the ending of problem A, but it's actually almost easier to just start this problem new. So we need to find the initial concentration of N2O4 at the time that the volume was reduced to 2 liters. So if we're starting with 1 mole of N2O4, and we're putting that in 2 liters, that gives us a concentration of 0.5 molar. So again, we'll use that as our initial concentration of N2O4. We'll assume that we're starting with 0 of the NO2, and we'll let this adjust to equilibrium. Again, since we have only reactants, we're going to have to push the reaction forward by having a minus x as our change for the reactant and plus 2x for the product. The equilibrium concentration for N2O4 should be 0.5 minus x, and it should be 2x for the NO2 gas. So 40 is equal to 2x squared divided by 0.5 minus x. Again, we're going to need to do some algebra here, so let's multiply through. And rearrange it so that it looks like the quadratic equation. Where we have 4 as our A value, 40 as our B value, and negative 20 as our C value. Writing the quadratic equation out and then plugging in our values for A, B, and C. We find that the positive root for x is 0.4772. What would be the fraction of N2O4 left undissociated? So again, we want to put the equilibrium concentration of N2O4 divided by the initial concentration of N2O4. The equilibrium concentration of N2O4 is actually 0.5 minus x. Which is 0.0228 molar. And this time our initial concentration was 0.5 molar. This gives us a fraction of 4.56 out of 100, or 4.56% undissociated at the equilibrium position. This concludes problem 2.